These are the notes on half-life and rate of decay. It might be helpful to have a calculator available for these notes. So as we're talking about nuclear chemistry and how atoms can become more stable, the probability of decaying is when an unstable nucleus eventually decays through one of the radioactive decay processes. So we've talked about alpha decay, beta decay. Those are really the two. Gamma decay is energy, so the particle isn't actually changing. But the radioactive decay of any single unstable nucleus is unpredictable, kind of based on a couple of things. So if you have a sample, you don't actually know when when one specific particle is going to decay. And so the decay occurs as a negative exponential function. Another way to describe radioactive decay is through a quantity called half-life. And so we're not going to actually do the math of the functions for this, but we're going to look at half-life, which is the amount of time it takes for half of a radioactive isotope to be likely to decay. With that, we can't know for sure that that much is going to decay. We don't know which particles are going to decay, but it kind of gives us some information about the likelihood that half of the particle has decayed. So an example of alpha decay, we have a parent nucleus, uranium-238, that is going to undergo alpha decay by losing a helium atom, and it's going to be left with the daughter nucleus, which is more stable, thorium. So whatever the half-life is of this uranium-238, we can expect that after that amount of time, half of the parent nuclei have decayed into that alpha particle in the daughter nucleus. The other half is going to remain. And so it's a way of us to be able to quantify how likely an amount has decayed, even though it is kind of a probability game. And so as we look at this, we're looking at time 0. And so this is number of half-lives. That could be this amount of time, whether it's a second, whether it's a year. It depends on the atom. But at 0 half-lives, the percent of the isotope, we have only the parent isotope. After 1 half-life, whatever amount of time that is, half of that parent isotope has decayed into something else, but half of it remains, meaning that the purple, which shows the daughter isotope, that other particle, we're going to have half of our sample being that. After an additional half-life, we have 50% of that parent isotope. Well, after another half-life, we're going to be at 25%, and the remaining 75 is the daughter isotope. After that, 25 divided by 2, we have 12.5, and that continues on. And so though the parent isotope is never entirely gone, after a few half-lives, very little of that remains. Most of it's going to be that more stable, what they call daughter isotope. So as we're calculating half-lives, it's always that same pattern where we're starting with 100%. And after the first half-life, if we look at this example here, we have 20 milligrams. Well, after the first half-life, 50% or half of the radioactive element is still present. So we have that amount that is divided by 2. So we have half after that first half-life. After 2 half-lives, we're really taking that 1/2 and we are dividing it by 2 again. And so we will have 25% or a fourth of that radioactive element still present. After 3 half-lives, we take a fourth and we divide it by 2. That would be an eighth, or 25 divided by 2, 12.5% of that radioactive element is still present. And so it does depend on our sample size. In this case, we had a sample of 20. So after 1 half-life, it had 10. And then 10 divided by 2 after another half-life, it had 5. And so we can use this idea of that sample cutting in half to look at how much is remaining in some examples. So for that, we are going to kind of use an approach. We're not going to use any formulas. There are formulas online, but we are not going to use any formulas. We're going to kind of just come up with a way to organize the information and apply that idea of half-lives throughout. So looking at this first example, we have actinium-226, which has a half-life of 11 hours. if 150 milligrams disintegrates over a period of 55 hours, how much will remain? So as we're looking at it, it does not matter what our element is, but we know the half-life is 11 hours. We are going to look at a period of 55 hours for our sample, which starts at 150 milligrams. To do this, I'm going to make a little chart. I'm going to have my number of half-lives. And with this, we have kind of our starting value, which is 0. And then we're going to look at a couple of half-lives. Depends on how far we're going, what we might need. And then I know we're looking at an amount of time, and that time could change that unit we're measuring it in. This is talking about 11 hours, so I'm going to make my unit of time 11 hours. So we're going to have a starting time of 0, but after 1 half-life, that means that 11 hours would have passed. After 2 half-lives, that means another 11 hours passed. 11 plus 11 is 22. 3 half-lives, we add another 11. 4 half-lives, another, and 5 half-lives, another with that. So it looks like going to 5 half-lives is enough because this is having us look at a period of 55 hours. And so we are trying to figure out what amount of our sample is going to remain. And we're going to measure our amount in milligrams because it gave us milligrams. And we know that at the start, we have 150 milligrams. And now I can figure out, well, how is that going to change as I go through 55 hours of time, which is 5 half-lives. And so our math on this is fairly simple, just in that we are going to take 150. Well, if after 1 half-life, this is going to divide by 2. Well, 150 divided by 2, at 1 half-life, we have 75 milligrams remaining. After another half-life, what's going to happen? Well, my 75 now is going to be divided by 2, and I get 37.5 milligrams. Another half-life, to get to us those 3 half-lives, divide that by 2, we have 18.75. Another half-life, divide by 2, I've got 9.375. And to get to that 5th half-life, 55 hours would have passed. One more, divide by 2, and we get 4.6875. And so how much is going to remain? 4.6875 milligrams of that unstable actinium-226 remains. The rest of that has undergone that process of becoming something more stable. So we're always going to kind of use, we're not doing anything with our with a formula. We're always going to kind of use this setup as we are looking at how can we model and show the changes of that sample as it undergoes that decay. So let's look at another example. If you want, feel free and try this on your own. Kind of copied over my chart. We might need to change our units of time and our units of amount based on what it's giving us. But we're always going to start with having 0 half-lives and 0 time, and then we can add on however many half-lives we need to show how much time has passed and what amount of our sample remains. So let's go through and read this problem. Scientists use carbon-14 to find how long ago an organic sample was living. And this is what carbon dating is. Carbon-14 has a half-life of 5,715 years. If there is 25 grams left of what was originally a 200 gram sample, how long ago did the tree live? So this one, the information we're given is a little bit different. I am going to look at half-lives. My time, I was told my half-lives is in years. And so we have time 0. And as each half-life passes, I'm going to add another 5,715 years. So I've got 5,715, and then I can add another 5,715. So that would be 11,430 plus another 5,715. And I'll do one more just because I'm not sure when we are going to need to stop. We can always add more as we go. So we're just adding that half-life, adding another 5,715 years as we go. So after 4 half-lives, this is how much time has passed in years. The problem is telling us there's 25 grams left of what was originally 200 grams. So my original amount is 200 grams. We want to look at now, when are we going to get to 25 grams with that? And so we know if we're starting with 200 grams after 1 half-life, well, 1 half-life, I'm going to take that number and I'm going to divide it by 2. After 1 half-life, 100 grams is going to remain. So it had to be longer than 1 half-life. Let's go through another half-life. Well, we have 100. If we divide that by 2, 100 divided by 2 is 50. We still haven't reached that 25 grams. So let's go through another half-life, divide by 2. I get that 25 grams, which is what the problem was asking about. So how long ago did the tree live? Well, if it's at 25 grams, that means that 3 half-lives have occurred, and the tree has been was alive 17,145 years ago. That is actually how carbon dating is used to determine how long ago something was living. All right, so what does this information tell us? We can find information about how much a sample is left. As our focus in chemistry is on things becoming stable, the length of a half-life and stability, every unstable isotope decays at a different rate. And the length of that radioactive decay is an indicator of stability. So if an atom has a short half-life, that means that it's not going to take very long for half of that sample to decay. That means it is a less stable isotope. Something with a longer half-life is a more stable isotope because it's taking longer to get to that point where half of that has decayed. And so if we look, and it doesn't matter what type of decay is happening, any type of decay indicates instability, but we have our different nuclides. Gold 198 undergoes beta decay. Well, it has a half-life of 2.695 days. That's pretty quick. So that is a pretty unstable isotope. But if we look at something, and these are nope, they're not totally increasing. But if we look at something like uranium, well, this is 1.592 times 10 to the 5th years. That's a long time. That's a fairly stable isotope compared to something like that gold. So we can use that information to rank stability based on what we have. So determine the half-life of each isotope and then ranking from least stable to most stable. So let's go through. We've got radon 222, finding that on our chart. Radon 222 has a half-life of 3.823 days. D is for days. Uranium 233, I've got alpha decay, and that is 1.592 times 10 to the 5th years. Uranium 235, 7.04 times 10 to the 8th years. That one was right here. Francium 220, we've got 27.4 seconds. That's pretty quick. And calcium 37, which is right here, 182 milliseconds. That's like a millisecond is a thousandth of a second. So it'd be like 182 times 10 to the negative third seconds. That's not correct scientific notation. So as we're ranking from least stable, well, if something is least stable, it's going to have a short half-life. And so as we look, we've got some seconds on here. Well, this is 27.4 seconds. This one is less than a second because it's milliseconds. So that calcium is going to be the least stable. Then our francium. And as we look now, those were our seconds. Now we've got our radon has a half-life in days. So I would say that one is next. And then comparing these two, 10 to the 5th and 10 to the 8th, 10 to the 8th is going to be a larger number, so that means uranium-233 is next. And our most stable would be that uranium-235 because it has a longest half-life. It doesn't mean it's the safest. It just means that it, as an atom, is more stable. So how is half-life used? Half-life is used, we talked a little bit about carbon dating, but there are different nuclides that can be put into your body. And depending on their half-life, they can be used for imaging, or can be used to see how is your body consuming things. Is it consuming at the correct rate? Half-life is also really applicable for medications, because if you're taking a medication, how long is it going to take for half of that medication to be processed, and so on. So feel free to look at some of these. They might relate to you depending on what you've kind of had happen in your life. For practice, there is a worksheet and a check-in. You're also going to do a pivot on types of radioactive decay and half-life. Reach out to your teacher with any questions.